So here's some prefixes. There's several of them. They go up in orders of magnitude and they go down in orders of magnitude. And they generally go in steps of 3 orders of magnitude or steps of 1,000th. Okay, if we look at the base unit, let's say the kilogram. Kilo means 1,000 times a gram. So really the base unit is a gram, and a kilogram is 1,000 times that. Okay, but we don't buy generally grams of flour and grams of sugar. We might buy grams of spices, but we buy things in kilograms. So most commercial things that we do are based on kilograms. So a kilo, which has the symbol K, if you look on the left side about third from the bottom, you see the kilogram. So that's 1,000 times a gram. So 1,000 can be written in scientific notation as 10 to the 3rd power. What that means is 10 with 3 zeros after it, or a 1 with 3 zeros, right? 10 times 10 times 10, that's what 10 to the 3rd means. If you go up and say, okay, I've got 1,000,000 kilograms, or I have 1,000,000 grams, okay, that's a megagram, and that is represented by the letter M. So that would be a 1 with 6 zeros behind it, or 1,000,000, or 10 times 10 times 10 times 10 times 10 times 10. Hope I did it 6 times. Okay, so that's what a megagram is. Now most of you probably never think about megagrams. You probably think about megabytes. Okay, so a megabyte is a unit of memory that we use in computer lingo. In fact, most of you don't even talk about megabytes anymore. You talk about gigabytes. We have gigabyte memory sticks, multiple gigabyte memory sticks. They're now on the market in 2007. You can get a 4 gigabyte memory stick for under $100. Okay, I bought a 1 gigabyte memory stick back in about 3 or 4 years ago in 2004 or so, maybe it was 2003, and it cost $260. Okay, and that was a big deal. I mean, that was a lot of memory, and that you can hang around your neck in a small USB memory stick. But now that's not a lot. And you know, of course, we have the iPods. We have the iPod Shuffle, and that's today, 2007. That's about a gigabyte, and it holds 250 songs, about 17 hours worth of music with standard compression. Now, there's also the iPod video systems. My son has one, and I believe it's 80 gigabytes it can hold. So it's a huge amount of memory, and it's about the size of a deck of cards. So, you know, now we're talking more about gigabytes, and a gigabyte is a 1 with 9 zeros behind it. So you multiply 10 9 times, and that's what a giga is. And you can have a gigabyte, a gigagram, a gigasecond. You can use that to describe large things, large amounts of things. And we should talk about tera too, because you can buy hard drives now that are terabytes, or hard drive systems, which may consist of several hard drives. Now, 3 years ago, I would have said I'd never need a terabyte of storage capacity for my home computer. But I have 1/4 of a terabyte now at home, 250 gigabytes, and I filled it up. So what am I to do? Well, why do you fill them up? Well, a lot of videos, downloaded videos, music, they take up a lot of space. Images take up a lot of space on the computer. Basic information doesn't take up much space at all. But a terabyte is now a useful term to know, and that's 10 to the 12th, which is 10 times 10 times 10. You do that 12 times, or it's a 1 with 12 zeros after it. Okay, and we don't really go much past tera when we're talking about things. going on the large size. Now, the course that you're taking and that you're thinking about is on the small side. So we went from kilo to tera. Now we have to go down. We have something called hecto, which is 100 times a gram, for example, or deca, which is 10 times a gram. Like you can have a decameter, which is 10 meters, or a decagram, which is 10 grams. Those aren't commonly used. Hecto and deca aren't used very often. In fact, if you talk to a scientist and you talk about hecto, they may not know that. Now, hecto does occur when you're talking about land, because it's a convenient unit. But generally speaking, hecto and deca aren't used much. Deci's used a lot. A decimeter, that's a tenth of a meter. But centi is used even more. A centimeter is about a half an inch, a little less than half an inch. It's a very common unit to measure the size of, say, your screen on your TV. If you're in Europe, they might quote screen sizes in centimeters. Maybe dimensions of your body. So when you buy clothes, how many centimeters is your chest, your neck, your arms, and you can buy a shirt, for example, and that would all be in centimeters. Here in the US, we use inches. Millimeters, commonly used. That's 1/10 of a centimeter, or 1/1000th of a 1/1000th of a meter. Now, I just noticed something wrong on this graphic. It has it as a capital M for millimeter. That should be a small m. It's actually mm. And centimeters the same thing, and decimeters the same thing. Those should be small letters. Okay. Now, when we start talking about microsystems and MEMS devices, we usually measure the components in terms of microns. A micron is 10 to the minus 6, or 1/1,000,000th of a meter. Now, you might be thinking, okay, I understand 10 to the third. That's just 10 times 10 times 10. But what's 10 to the minus third, or a millimeter? That's not 10 times 10 times 10. It's 1 divided by the quantity 10 times 10 times 10. Well, that's a little harder to conceptualize. Or you can say it's 0.1 times 0.1 times 0.1. A tenth times a tenth times a tenth. That might be a way to look at it. So if I take my meter, if I have a piece of paper that's 1 meter long, and I cut it in 10 pieces, okay, then I have 10 equal pieces. Then I take one of those pieces, cut it in 10 pieces again. Now I should have a centimeter. No, I'm talking equal sized pieces. So I should have about a centimeter. Okay, so what did we do to get to a centimeter? We cut a piece of paper that's 1 meter long into 10 equal parts. Then we cut one of those parts into 10 equal parts. So now we have a centimeter piece. Each piece is a centimeter. We take one of those centimeter pieces and cut that into 10 equal parts, and we have a millimeter. Okay? And that's not easy to do. Take a pair of scissors. But now if we go to a micron, we take one of those 1 millimeter pieces of paper and we cut that into 10 pieces, and we take one of those pieces and cut that into 10 pieces, take one of those pieces, cut that into 10 pieces. Now we have a micron sized piece of paper. Well, we can't do that. You can't cut something that small. You know, it's very hard to do. Unless you have very, very sophisticated equipment, you can't make something that's a micron big by cutting it. But we manufacture things on the micron scale all the time. And that's really cool. How do you make something that's a micron big? You can't cut it to that size. You have to use different techniques to do that. Okay? And you'll learn later on that there are methods called photolithography and chemical etching and chemical vapor deposition and Liga and processes like that where you can actually create extraordinarily small devices. okay, that are a micron in size. So that's 10 to the minus 6. So that's a millionth of a meter. To give you an idea, a hair is about 100 microns, 80 microns, around there. Okay? Well, we keep going smaller when we talk about nanotechnology and microtechnology. The next unit after the micron is the nanometer. And that's written with a small n and a small m, nanometer. For distance, the unit prefix or symbol is a small n. So nano is a billionth. So it's 1,000th of a micron or billionth of a meter if you're talking about a nanometer. You can talk about a nanogram, you know, very small unit of mass. And normally I stop talking about things at the nanoscale, but you know, I ran across an article where they made a micron-sized device that could measure attograms of mass. So, you know, you can measure things that are 1 times 10 to the minus 18th of a gram, and that's the attogram. You can, generally you don't measure distances that's that small, but if you do, you're talking about distances that are within the nucleus of an atom. Okay, pico, 10 to the minus 12, femto, 10 to the minus 15. We use those units a lot when we talk about time. We can measure very fast events, chemical events, things, you know, how long does it take for 2 molecules to combine and create a new molecule? Well, that might be on the picosecond time scale or the femtosecond time scale. Very, very fast events. How long does it take an atom to release a photon of light? You know, for the electron to go from one orbital to another and release a photon of light. That takes a very short amount of time. So you need very small units to do that. Now, I have not seen anybody use zepto or octo or yocto yet. So, but atto, you know, we've gone all the way down to the atto. But I'd really like you to understand the differences between nano, micro, milli, centi meters in terms of distances. We use it all the time. So you should be able to convert from nanometers to microns, from millimeters to nanometers, those sorts of things. And you will be quizzed on that if you take the course with me. So, using prefixes. So here are some examples. If you've got 2,000 meters, okay, that's 2 kilometers, right? There's 1,000 meters per kilometer. If you have 0.005 meters, what is that? Well, that's 5 times 10 to the minus 3. Okay? So if you take a 5 and you move the decimal place to the left 3 times, that's 0.005. Okay? So you're talking about a millimeter, right? 10 to the minus 3 is a millimeter. Okay? You can write it as 5 millimeters or mm. Talk about amperes, very small units of amperes. Milliamperes is a pretty common unit. If you move that decimal place to the right, you can convert from amperes to milliamperes. So 0.025 amperes is 25 milliamperes, and it's written with a small m and a large a. Since a kilogram already uses a prefix, kilo, smaller or larger values are based on the gram. And we kind of alluded to that in the previous slide. So 0.015 kilograms is 15 grams. Move the decimal place 3 places. Okay? And, you know, we're writing it 15 times 10 to the minus 3 kilograms. That minus 3 should be a superscript. It should be raised up a little bit higher. That's the proper way to write it mathematically. So why is it important that we standardize on some system? Well, here's a story NASA tells people why it's important to know your units. It's an embarrassment, however, for NASA. But in September of 1999, NASA's Mars Climate Orbiter probe was lost. After a 286-day journey to Mars, they probably spent 10 years building this probe. Okay? Probably, 20 engineers and 50 technicians worked on this project. Different components were built by different companies. I mean, it was probably a big deal. Hundreds of millions of dollars, I'm sure. Okay, so it took 286 days for this probe to get to Mars. When it got to its final approach, it fired its engines to move into orbit, and it brought it closer to the planet's surface than planned, preventing the orbiter's engines from functioning properly. So the orbiter fell deep into the planet's atmosphere and burned up and crashed. Ooh. A thorough investigation discovered that the loss of the $125 million orbiter was due to two different units of measurement. NASA used the metric system, right? NASA is scientifically based. All the scientists use the metric system. However, the team that provided the thruster data, and did the thruster calculations, used an English system. And nobody wrote the units down. So that's why I will mark you off if you write an answer down 1.7. And if you write down 1.7 microns, you're good. If you write down 1.7 times 10 to the minus 6 meters, you're good. So please include units whenever you write something. So other than science and technology, the U.S. system of weights and measures is still used by citizens of the United States. We still drive in miles per hour rather than kilometers per hour. We still weigh ourselves in pounds rather than kilograms. Okay? So how do you feel about that? Converting to the SI. We tried to do it back in the 70s, but it didn't work. I remember seeing signs on the road that would give you the distance between towns in both kilometers and in miles. And what do you think the biggest roadblock to converting to SI is? Well, one thing is you got to change all the labels. That costs businesses money. If you're used to buying, 10 ounces of something and you convert it into grams, and you're not used to grams, you may not buy that something, or you may not understand if it's a good value or not because you're used to ounces. That could be one roadblock. And if changing all of the labels over from ounces to grams for a company can cost a lot of money. You've got to reprint the labels. You've got to, educate your public. And, if you have a 10-ounce jar of marmalade and you switch to grams, for instance, and you say, okay, now I have a 280 point something gram jar of marmalade, people are going to go, huh? So you'll probably want to round it off to 300 grams, just because it's a nice round number, but then you got to charge more for it. And the consumer will see this jar of marmalade that's slightly, they may or may not notice it's slightly bigger, but now the cost is more. Then they look to the next one, and the other company's still selling 10 ounces, and it looks about the same, but it's cheaper. So now you're going to lose business. Okay, now you go to 250 grams instead of 280 grams to be 10, kind of close to 10 ounces. Now you get less product. And, people get set in their ways when they're buying products. So, it's a difficult thing to do. So one roadblock could be, just changing labels over. Another one is re-educating the public. Most people prefer to deal with ounces rather than grams because they're used to it. Don't fix it if it ain't broke, the old adage. And I'm sure you can come up with some other ones. So last but not least, in summary, we've been using units of measurements at least to 3000 BC, which is about 5,000 years ago. We may have actually used units and measurements further back than that. Anytime someone has to exchange something of value, they're going to want to know from one day to the next if they're getting the same deal. So they need some way of comparing the mass or the weight of something or the amount of something to see if they're getting, good deal. And it's driven by trade. So these weights and measures have been derived, defined, redefined, replaced, evolved into the international quagmire through the years. this has created a lot of problems with international communication and commerce. In 1790, the French Academy of Sciences developed the metric system. In 1960, the GCWM, and they call it the CGPM conference, declared the modern metric system as the International Standard of Units, or SI, System International. The SI consists of 7 fundamental units and additional derived units, each of which use common multipliers of powers of 10 to represent smaller and larger quantities. So we talked a lot. I suggest you do the corresponding reading that's associated with this presentation, and I hope you have a feel for how important scale and units and measures are to your future as a microsystems technologist.